Good morning. Today we're going to talk about three very important concepts in physics, which are Newton's three laws of motion. Sir Isaac Newton was one of the greatest scientists who ever lived, and he lived at a time when there weren't a lot of machines and technology that you could use. He just had to use his brain. He came up with a number of great discoveries, and the ones that we'll look at today are laws that govern how things move. There's three basic laws. Newton's first law: objects in motion tend to stay in motion, and objects at rest tend to stay at rest, unless they are acted on by unbalanced forces. Newton's second law is a mathematical equation: force equals mass times acceleration. And Newton's third law is that for every action, there is an equal and opposite reaction. So let's look at Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion, unless they are acted on by an unbalanced force. This is sometimes known as the law of inertia. And inertia is a tendency of an object to keep on doing what it's doing, to not change, to resist change to its state of motion. In other words, if an object is sitting still, it tends to stay that way. It doesn't want to start moving. And if an object is moving, it doesn't want to stop moving or change its motion in any way, and will only do so if some unbalanced force forces it to either start moving or change its motion. Now, it's obvious to us that a book sitting on a desk is not going to move unless you push it, or an earthquake happens, or the table breaks. There has to be some reason for it to move. But it seems a little less obvious to us that an object that's moving will move forever, because that's not what we see. We roll a ball down the street and it comes to a stop. Even if you're playing hockey on a smooth, icy surface and you hit the puck really hard, it will eventually come to a stop. And that's because there are unbalanced forces acting on it. The unbalanced forces we've already talked about: friction. Now, inertia is in some ways like momentum. We said momentum is a property of a moving object. Moving objects, if they're big and they're moving fast, are hard to stop. Inertia is kind of like that, but it deals with things that are not moving at all. Momentum, you have to be moving, but inertia is a property something has. The more mass you have, the more inertia you have. It's harder to kick an elephant and make it move than a ping pong ball. Why? Because the elephant has much more mass and therefore much more inertia. A heavy truck, and you're driving a heavy truck and you slam on your brakes, it's going to take longer for it to stop because it has inertia. It's also going to be harder to get it going up to a certain speed when it is stopped because of inertia. So in conclusion, an object wants to keep on doing what it's doing, and it's going to keep on doing that unless an unbalanced force causes it to change. So a little review: this is a balanced force. The book sitting on the desk, gravity is pushing it down, but the desk is pushing back up with the same amount of force. How do we know it's the same? Because the book is neither falling nor rising. It's just staying right where it is. The forces are balanced. However, if we suddenly put a force on the left, pushing it toward the right, and we ignore friction, there's no friction, this is a completely slick desk here, it's going to move. It's going to move because there's no force opposing this rightward force. So it's unbalanced. Examples: soccer ball sitting on the field, nobody kicking it, it's not moving. Someone kicks it, that's an unbalanced force. There's a lot of force on one side of the soccer ball, but not that much on the other. The soccer ball will move. A tug of war: if both sides are pulling with equal force, nobody moves. But if one side gets tired and suddenly the force that they're pulling with is weaker than the force the other side is pulling, now it's unbalanced and we have a winner. Inertia explains something like this. You might think that if you're in an open back of a truck and you throw a ball up in the air, that the ball is, you're going to just keep on going and the ball will be left behind. But look what happens. The ball continues moving with the speed of the truck. The ball was moving. It had motion. in the truck. Now, relative to you sitting in the back throwing the ball doesn't look like it's moving, but to anyone watching it, it was moving. It has motion. Therefore, it has the inertia that will keep it moving. And when you throw it up in the air, yeah, it goes up in the air and it comes down, but it's also moving with the speed of the truck. That's inertia of a moving object. Inertia of an unmoving object would be you trying to push a car. It's not going to be easy. It's stopped and it wants to stay stopped. You have to put enough unbalanced force on it to get it moving, which you may or may not be able to do. Now, where inertia is especially important is in car accidents. You're in the car. You don't feel like you're moving, but you are. However fast the car is going, you are going at that motion as well. If the car suddenly comes to an extreme stop, like hitting another car or a wall or a tree, the car has had a force put on it, and that caused it to change its motion. You, inside the car, did not hit the tree or the wall, so you are still moving. Inertia is moving you at 50 miles an hour. And you will continue moving at 50 miles an hour until something puts a force on you, like the dashboard or the windshield. This is why we have airbags and seatbelts, to account for the fact that inertia will keep you driving at whatever speed your car was going and slow you down in a way that will hopefully keep you alive. Look at what happens if you're hit from behind, right? So you're hit from behind, the car moves forward very suddenly, but you sitting in the car, let's say your car was stopped, somebody hits you in the rear, your body is still trying to stay motionless. So your head snaps back because there's nothing there stopping it. The rest of your body moves forward because the seat is pushing against it. When the seat moves forward, it pushes the rest of you too, but your head doesn't have it there. That's why we came up with headrests, to make sure your head doesn't snap back, because as you can imagine, this could break your neck. Now, you've probably seen inertia demoed in things like here we have eggs balanced on tubes on top of a tray. He hits the tray really hard, and the eggs stay where they were until gravity forces them down into the water. So the eggs have inertia. Since the force put on the pan was not on them, they just stay right where they are. And then a new force comes along, gravity, pushing them down. And since they don't have the tubes anymore to push back, they drop into the water. Now, I love this next one. These two German kids decide to do a classic old trick where you have like a table full of dishes and everything, and you pull the tablecloth really, really fast enough that the force on them, on the plates and everything, is not enough. The friction is not enough to drag them with it. If you pull it slowly, they don't fall off, but if you pull it fast enough, they stay in place. And let's see how it works out. Okay, so it didn't work out that great, but notice the trick did sort of work. I mean, the stuff is there up until the point where the wall unit crushes all the plates and the table and his little brother. The little kid's okay. Now, again, you may ask, if objects tend to stay in motion, why don't they move forever? And it's because there are always, almost always, unbalanced forces acting on them. Friction being one of the main ones, or gravity. You throw the ball up in the air and it doesn't keep on going because here on Earth, gravity will bring it back down. Now, if you're in outer space, things are a little different. If you're far enough in space that gravity is no longer there, you have to be very careful in what you do, because if you just got up out of a chair the way you do here on Earth, gravity holds you down. In outer space, you'd jump out of the chair and you'd keep on going until your head hit the ceiling. So astronauts in space have to be very careful about how they move. Newton's second law is a mathematical equation. Force equals mass times acceleration. F equals ma. Force, mass, acceleration. And remember, again, acceleration is a measurement of how quickly an object is changing its speed. So let's imagine you drop a ping pong ball from a first-story window. It has a certain mass. It's accelerating from gravity, 9.8 meters per second. If you multiply 9.8 times the mass of the ping pong ball, you get the force that it will hit the ground with. Now imagine a bowling ball. The acceleration is the same. Gravity is the same no matter what. But the mass is much greater. So the force is going to be much greater too. And there's a big difference between having a ping pong ball from a first-story building hit you on the head and a bowling ball. So again, the implications of force equals mass times acceleration are a lot. Something can be very slow, like a glacier. A glacier is a mountain of ice. They move just a few inches every week, but their mass is tremendous. Imagine a mountain made out of ice. How much would that weigh? How much mass would that have? The fact that it's moving slowly, okay, but take that speed, multiply it by the tons, the millions of tons that are in that glacier, and you have a tremendous force. Glaciers can carve right through mountains. They're pretty unstoppable. They're slow, but they have a lot of force. They have changed the surface of the earth. A bullet is very small, but it has a fast speed. It has a high acceleration. So if you take its acceleration times its mass, you still have a pretty big number. On the other hand, if you have something small and not changing speed very, very quickly, not a lot of force. F equals ma is something we use in sports a lot. I mean, something like golf. You are putting a force on a small mass, and depending on how much force you use, it's going to accelerate at different speeds. And the whole trick to golf is you have to think about how hard do you hit it to get it to accelerate fast enough to go to the place you want it to go to. So to illustrate force equals mass times acceleration, F equals ma. Here's a small ball. If I want to take this ball of pretty insignificant mass and cause it to accelerate, I have to put a force on it. If I put a greater force on it, it's going to accelerate at a higher rate. But what happens when the force that I apply is on a much greater mass? This bowling ball is many, many times heavier. It has more atoms, it has more mass than the small plastic ball did. If I try to apply the same amount of force on it, it does not accelerate nearly as much. And also I've hurt my hand. So if the force is equal, but the mass is greater, the acceleration will be less. If the force is greater and the masses are the same, the more force, the more acceleration you'll get if the masses don't change. There's a balance between all of these, and it makes logical sense. I mean, you know, if you kick a light object, it will go flying through the air. But if you kick a car, it won't. So this formula may seem complicated, but if you think about what it's saying, it makes perfect sense. You might even say, was this really a great discovery? Didn't people already know this? Well, they knew conceptually that yes, if you put more force on something, it will move faster. But this formula allows you to calculate exactly and precisely how force, mass, and acceleration are all tied together. Newton's third law says that for every action, there is an equal and opposite reaction. Now, what does this mean? We sort of mentioned this before. We said if a book is lying on the desk or if you're sitting in your chair, you're putting a force down on the chair and the chair is putting an equal force in the opposite direction on you. This third law can be misunderstood in some ways because people will say, well, wait a minute. If the forces are balanced, then how, for example, do we swim? Because it takes unbalanced forces to get motion. You're saying I'm pushing against the water and the water is pushing against me equally. Those would be balanced forces, and therefore doing this should not actually get me moving. But that kind of fails to understand exactly where the forces are going. Yeah, I'm pushing against the water with a certain force. The water is pushing back equally, but it's pushing back on me. See, these are not balancing out because they're not acting on the same object. I'm acting on the water is acting on me. When I push back on the water moves. I'm putting an unbalanced force on the water. The water is putting the same onto me. That's an unbalanced force, and it pushes me forward. So we do get motion because although the forces are equal, they're not really balanced. So look at this jellyfish. Jellyfish is moving, pushing back against the water, and as a result, the water pushes the jellyfish forward. The skateboarder pushes against the earth with his foot, and the earth pushes his foot equally and he goes forward. If he pushed back harder, he'd go forward faster. And there's lots of examples on YouTube of people who don't understand this whole equal and opposite thing. If you hit the bat on the piano is going to exert a great force on that bat. It might be enough if you're not careful to slam it right back in your face.
Go.
In the movies, people can punch through walls, but in real life, if you keep punching the wall is punching your hand just as hard. The harder you hit the wall, the harder it hits against your hand, and you're probably going to lose that fight. So, in review, Newton's first law, the law of inertia. An object that is not moving will never move, and if it is moving, it will never change its motion unless unbalanced forces cause them to change. Newton's second law, force equals mass times acceleration. Hitting an object harder will cause it to accelerate faster. Hitting two objects with the same force will cause the smaller object to accelerate faster. And Newton's third law, for every action, there's an equal and opposite reaction. Thank you very much.